Okay, what questions do y'all have this morning? Yeah. Okay, first time that's up. So we got flat and black. So we got ln of x equals 5 minus x, and we want to get a solution to this expression. Newton's method gives us ways to find roots of things. So what we're going to have to do is we're going to have to make this so that we want it equal to 0 and then solve for that, right? Okay. We're going to set f of x equal to 5 minus x minus ln of x. And then if f of x is 0, this statement is true. Okay, so we'll try and figure out a root for that. The other thing we could have done is we could have done some algebra, and maybe that's the easier way. I'm not sure yet. We might have to come back, but you could get that x equals e to the 5 minus x as well. Subtract the x over 0 equals e to the 5 minus x, and that might be easier to use Newton's method with. I'm not sure yet. In fact, it probably is, because the derivative of that is a lot easier to work with. So let's do this guy. That way, I mean, the algebra here is not bad, but I think the algebra up there is easier. So xn plus 1 equals xn minus f of xn over f prime of xn, right? So xn plus 1 equals xn minus, in this case, our function's not going to be this. It's going to be e to the 5 minus x, right? Divided by e to the 5 minus x with a minus sign on it, because the derivative of that has a chain rule component to it. And then I've got a minus 1. Good. Okay, so we want to start with 10 and find x2. So x2 equals 10 minus e to the 5 minus 10 minus 10 over minus e to the 5 minus 10 minus 1. So this is round to 6 decimal places. Okay. So there's our first one. So let's approximate this to quite a few decimal places. Well, if I get a common denominator on the 10 here, I think we might have some cancellation stuff, because I could do plus, plus, plus. I could do that. This will be e to the 10 e to the minus 5 plus 10 plus e to the minus 5 minus 10 over e to the minus 5 plus 1. Tens cancel, which is nice. Yeah. Are you good with the plus signs? Okay. Okay, we had this to start with. If I distribute this minus sign, it's a fraction here, right? So if I want to make a fraction negative, I either make the numerator negative or I make the denominator negative. I'm just going to make the denominator negative. And then this minus sign distributes to both of those to make them positive. So that's the first bit. Right. And then the next bit, I'm going to find a common denominator. Here's a fraction. Here's something that's not a fraction. So I want this to have the same denominator as that does. So I'm going to multiply the top and the bottom by e to the minus 5 plus 1. And put them over the same denominator. And then if I distribute that 10, comes in here, I can cancel the 10s. We got 11 e to the minus 5 over e to the minus 5 plus 1. Good. Okay. Let's go ahead and put this into our function again. So that goes x2. Sorry, this was x1, wasn't it? This was x1. Because all 10 was x0, right? So x2, that's going to be this whole thing plus 1 minus e to the 5 minus that thing again, 11 e to the minus 5 over e to the minus 5 plus 1 minus 11 e to the minus 5 over e to the minus 5 plus 1 over e to the with a minus sign out front, 5 minus 11 e to the minus 5 over e to the minus 5 plus 1 minus 1. All good with that? And then we just carefully type things into the calculator. Which, yeah. I want. That's the thing that I'm going to have to type several times, so I'm just going to copy paste it. Goes there. I go a minus. It goes there. I do that. I divide. The pink parentheses went away. Does that mean I fixed them? Probably. I have a minus. I have it again. I have a -1. And we end up with $4.852757. They want us to interpret it like that. Is that what I want it to interpret it as? I don't think that's what I want it to interpret it as, is it? No, certainly not. Am I missing a parenthesis somewhere? I put a times in there. Unless it's doing the simplification for me, but I don't think 4.85 is the answer that I want either. Sometimes the e-dx function is written as exp of something. So we'll try that. Now it's saying these parentheses aren't working. So maybe I need to check my parentheses. Because it's certainly not just -5. With the natural log one? Okay. Okay. And then you don't have any exponentials. All you have is arithmetic or algebraic stuff because you got your derivatives 1 over and you just have the one natural log everywhere. Okay. You should get the same, you should get approximately the same answer. And if you're just looking for it up to 6 decimal places, then I wonder if it even, there's only one. If the question is asking us to be accurate to 6 decimal places, I wonder if it's actually accurate to 6 decimal places. Probably not. Otherwise, it wouldn't tell you to use Newton's method. So, okay. So that's the actual solution accurate to 6, but Newton's method only approximates it. Let me try one more time to type this in. Let's go. Y equals. Well, that's what I want, but it doesn't give me a decimal approximation. It's right in there, just a little bit bigger than 3. That's good. About come on. I need one more decimal place. E to the minus 5. Yeah. That doesn't make any sense at all. All right. You said doing it with the natural log was easier. So we've got f prime of x is minus 1 over minus 1 over x, which we can write as minus x minus 1 over x, which is equal to 1 minus x over x. I like that sort of the best. And then we'll get x1 equals x0 minus f of x0 over f prime at x0, which is going to be x0 minus 5 minus x0 minus natural log of x0 over 1 minus x0 over x0. Okay. We put 10 in there. You get 10 minus 5 minus the natural log of 10 over minus 9 over 10. 10, I'm going to make this plus, and this plus. And then we're going to multiply everything by 9/10 to clear out denominators. The minus sign, and then plus 5 times. No, if I multiply by 9/10, that thing just cancels, right? But I still need to divide by 9/10. Plus 5, no, still minus. That's still plus. Okay, that's minus 9 plus 5 is minus 4 plus natural log of 10 over minus 9 over 10. So that's minus 40 plus 10 natural log of 10 over minus 9. Okay. X2 is this thing. What goes down here? 1 minus that, right? Okay, let's see if we can convince Wolfram to do this for us so we don't have to do all this arithmetic. So we're going to go x minus, what's our function? it is x naught minus 5 minus x naught minus natural log of x naught divided by 1 minus x naught over x. All right. That's what we get for x1. Okay. So we're going to tell it to do that at x equals 10. That's going to tell us the first thing, which is what we had there. And now we're going to tell it to do it at this thing, so that I don't have to type that all in again. I like that result form. Of those three forms, the result form looks like the easiest to type in. So we're going to do that one, minus 10 over 9. And then we're going to multiply by log 10 minus 4. Log 10 in this case is natural log. So let's do that. And it gives us this stuff. But it doesn't give us any approximations. Put in a bunch of zeros, see if it holds decimal places. Still only gives me to 5 decimal places. All right, now I'm confused. Maybe I should put in log here. Is the result 1.886 or 4.008? Is it trying to solve for x in this expression? That's probably what it's trying to do. Because that's the result. That's simplified form. So I bet we want the x equals this guy. Let's try that. That one's a lot closer to the actual answer anyway. 4.00893. Okay, let's do it this way. first do it at 10. We get 10 digits. And then we do it at that. Three 3.94, 9437, 18. Any thoughts on what we're doing wrong? How many of you carry? Do not round until the final answer, then round to 6 decimals. The 3-6 was the one that we actually tried to like solve and trick it, but that didn't work. Okay, let's not do 10 digits of that. Let's just use that. And maybe I write this as the derivative. So minus 1 over x. We'll write it that way. It's probably good that I wrote it that way because that's a different number than what we were doing before. Okay. That is my derivative, right? Minus 1 over x. I just couldn't differentiate or do some arithmetic early on. That's probably what our problem was. Okay, and now we get to plug in minus 10 over 11 times log of 10 minus 6. We want 10 digits of this. Correct answer is 3.68. And this gives us 3.81. Why? I think this is doing something completely different. Because I should be getting an equation. It's asking this thing equals this thing, not at. It's not evaluating it at this value. It's just getting rid of the word at and setting things equal to each other. I wonder if I can do a bar. No. Okay. 10 digits of, evaluate this at this. It's still doing the stupid thing. Okay, let's try just. Okay, so that's fine, right? That's what we want it to do. How about to 10 decimals? Okay, we're just going to copy and paste what it tells us and evaluate that. Okay. 3.689909. Okay, there we go. Wow, that took a long time. I am sorry that took so long. Should we see if we can do a similar question now that we know how to do this? So x is going to equal, well, it's going to x minus f of x. F of x is going to be 7 minus x. 7 minus x minus natural log of x divided by the derivative of that, which is minus 1 over x. Okay, and it tells us our starting point is 3. So we're going to say at x equals 3. And it's going to give us our first approximation. And we're going to tell it at x equals this thing, which is minus 3/4 of log of 3, natural log of 3, minus 8. And it's going to give us this. And then we take this and we evaluate it to 6 decimals. And so it's going to tell us that this is 5.32682. And we're good. So much easier that time. Other questions you guys have? Maybe. Use Newton's method to find the positive fourth root of 10 by solving this and starting with 2. So we're just going to do the exact same thing. And it wants us to find the second iteration. So we're going to have x, Newton's method says put in the function up top. So x to the 4th minus 10 divided by the derivative for x to the 3rd. And we're going to evaluate at x equals 2 to start with. You get 29/16, and then we'll put in 29/16. And we get that 2,777,203 over 1,560,896. We want a simplified fraction, so that's probably the simplified fraction that we want. Let me finish typing this in and then I'll show. Okay. Because when I put in x equals 2, it says 29. So you got xn equals xn minus 1. That's not a minus 1, it's a squiggle. Minus 1 minus f of xn minus 1 over f prime of xn minus 1, right? So if I just evaluate this bit, that's what I've got typed in to Wolfram here. I've got the xn, I'm just going to call it x, and I've got my function on top, which is x to the 4th minus 10. And then I've got the derivative of the function below it, which is the 4x to the 3rd. Okay. And so if I put the first approximation in there, whatever that evaluates to will become the next approximation. But because I've told the computer to evaluate it at that number, but it knows what that function is, all I have to do is change that number to the next approximation to get the next approximation out of the computer. Does that make sense? Okay. So I get the first approximation out after 2, and then I can put the 29 over 16 in to get the next approximation out. And this thing is approximately the 4th root of 10. So if I took this to the 4th power, I should get something really, really close to 10. Let's try that, see how close to 10 we are. We'll raise that to the 4th power. And it's pretty good. It's good to 2 decimal places. Yeah. Yeah, because a solution to this expression would be a 4th root of 10. There'd be a negative 4th root too, but you just put a negative sign on this fraction. The graph of that looks like that. Since we start at 2, we're going to come up and we're going to approximate this root, the positive one. If we'd started at negative 2, we would have come down to that one. Or straight up, down, straight up, down. Does that make sense? So if I wanted to try and figure out what, say I want to approximate the square root of 3. Well, what I'm going to do is I'm going to make an expression that is the root of, like x squared minus 3 equals 0. The square root of 3 would solve that, right? And so if I wanted to solve this to approximate that, I could use Newton's method on this. And so we can use Newton's method on that, and I can get, well, xn plus 1 equals xn minus x squared minus 3 over 2x. These are n's. And that's Newton's method. If I do this expression will, in its limit, go to the square root of 3. So like in Wolfram Alpha here, if I put in x minus x to the second minus 3 over 2x, well, a good approximation for the square root of 3 is probably 2. I will get a first approximation for the square root of 3, which it tells me is 7/4. And that's pretty good because 49 over 48 is pretty close to 3 if you square that. But if I do 7/4 into there, I get a better approximation. 97 over 56 is going to be a better approximation for the square root of 3. If I do it again, 97 over 56, I'm going to have an even better approximation, and so on. So let's see how good this approximation is. Let's take the square root of 3. We're going to subtract from it 18,817 over 10,864. So that's good to like 8 decimal places. Right. That's 9 zeros and then a 2. So just doing Newton's method, what was that, 3 times? You get 9 decimal places basically of the square root of 3, which is pretty good. So that's what that question in the assignment was kind of talking about. If I want the 4th root of 10, I can use Newton's method and get a really good approximation for the 4th root of 10. Other stuff you guys want to talk about? Is anybody online still around? Lost a lot of people on that. Nope, everybody's still here. Okay. You guys online have any questions? We can either start review for the exam Monday, or we can move on to 4.8. Or if you still have questions on this stuff, we can do that too. Anybody have a preference? Probably about 15 again. That means about 2 for each section. Maybe I'll make it 16 so there are 2 for each section. I hope it goes better again this time, so we don't have to do the retakes and stuff, but we'll see. It's been a weird semester. It's been tough. And I will try and pick ones that don't have that. I don't know if there are any from there, but if there aren't any from there that have only like 1 or 2 parts at most, then we'll just not do those. So. Right. I'll try and find one that kind of only has 1 or 2 parts from there. Maybe just find the critical points, or just find where the maximum is, or something like that. Yeah. Other questions about test stuff or otherwise? Yep, cumulative, yeah. the final will be like during finals week. Is that what you're asking? Yeah. I'm gonna give you a project probably early next week, and then I think after Thanksgiving, we have some time. I forget exactly what I've got allotted out, but I think there's some time where we'll just do project stuff, maybe 1 week. And then we'll see. There's kind of outbreaks and stuff popping up again. I know that the county or whatever the local health district is advising people in the area not to go into work if they don't have to, but campus is still pretty safe, it seems. So we'll see what happens after Thanksgiving, but we've been doing a good job so far. I'd hate to screw it up, but we'll see. If we can come back, I'd like to come back. I really don't like the online stuff, and this entire semester has not been my favorite style of teaching, but we're making do. We've got chapter 5, and then I just want to do like 1, maybe 2 sections of chapter 6. So I think 5 goes to 5.6. So like 8 sections left, which would be, if we do one every 2 days, that's like just over 3 weeks left. I just do the chapter 5 test, and those 2 sections would be maybe a little bit on the final. Those 2 sections kind of get you ready for Calc 2. Yeah, there. Area integration technique type things. Yeah. Right. Yeah, so we moved that back a week, and I originally had us plan to get through like all of chapter 6, but I think we're gonna be fine. That was ambitious, and we don't need to do that, so we're not gonna do that. But we can't fall too much farther behind at this point. But I think we have time to do that and still take some time for the project, just solo project. I forget what I have in the syllabus, maybe like 10%, something like that. I think there's like 1,000 points in the class, maybe, and it's worth 100. Does that sound right? The semester tests are 100. I think the final's 150. I think it's in the syllabus, and it's on the start here stuff in Canvas. Yeah. Sorry, this is the max you can. Yeah, you can get extra credit from the. Yeah, what was it? The chapter 1 homework was worth like an extra 12 points, and then there's like 3 extra sections to give you those, or maybe 2 extra sections. But since we're not going through all of those sections anymore, I'll have to adjust it, but yeah, you'll still be able to get, maybe it'll be out of 300 because we didn't do, I don't know how many's in chapter 6 altogether. There's 6.6, so there would be 4 sections that were probably in there that we're not going to actually get to do. So I'll probably take off like 40 points from the top end and 40 points from the bottom end type thing. But it's going to be using my MATLAB or MyLab Math or whatever it is where you do the homework. So it's not going to be the Canvas multiple choice again. That was just a fiasco or a disaster. So yeah, my lab math wasn't good, but it wasn't nearly as bad as it was from the multiple choice. So I think that's our least bad option. Other thoughts about how? I expect it to be about 3 pages, 3 to 5 pages probably, to thoroughly answer the question and talk about your methods. No, however you want to write it, it's fine. Yeah. 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 It just needs to address all of the issues, and I expect to actually thoroughly address the issues. It's probably going to be about 3 pages. Sorry? It's up to 3, yeah. So you can do groups, just not in person, kind of. I mean, I can't control what you do outside the classroom, but we're not going to work in groups in the class. But you guys can set up your own Zoom meetings and stuff like that, I think, can't you? Do you guys have that capability as students? Okay. So, yeah. Yeah, one of the projects I've done in the past, which this might be kind of similar to, is I give you some sort of like a business optimization problem, and you talk through, okay, you have to convince your boss that you want to do this thing so that you optimize profit or you minimize the cost of whatever you're producing or something like that. And you need to convince him thoroughly that that's the right thing to do. Other thoughts? Is this style of class going better than it was for the video stuff? Just the more lecture and then, okay. Okay. I am still posting all the class videos, but they're a lot longer, right? Yeah. Okay. Let's, there's only 15 minutes. I can't really get into much there, but anti-differentiations next. So undoing derivatives, getting ready for chapter 5. Chapter 5 starts talking about integration, which is anti-differentiation. So I can kind of give you a general overview of what calc does. So calc is 2 things. You're either looking at little pictures to try and get an idea about what the big picture looks like, or you're looking at a big picture and then focusing in on little details. And with differentiation, you look at the big picture and then you kind of focus in on a little detail and you get like what the slope of the curve is or how things are happening instantaneously. So that's like zooming in really, really far and trying to get an idea about what the whole thing looks like after you, because you have an idea what the whole thing looks like, and then you zoom in and you get ideas about what like the little details are. Okay. The other side to that is you have all the little details and then you have to put them together to get the big picture. Like, so that's the harder one, right? Because putting together a puzzle is a lot harder than like taking apart a puzzle. And so integration is integrating all of those little pieces together into getting the big picture. And it turns out that the fundamental theorem of calculus links integration and differentiation together really, really nicely. Like if you want to take the big picture and get the little picture, that's easy. Differentiation is the easiest thing to do. You can differentiate pretty much any function that you run across that you can write down. But the thing that you can't do is integrate any function or anti-differentiate any function. And there's some easy ones like e to the minus x squared. There is no function that I can write down that has that function specifically as its derivative. I can take the integral from 0 to x, not let's call this y and dy. And if I call this f of x, I mean, I can write that down, and the derivative of that is e to the minus x squared, but it has that integration piece in it. I can't just write down like, well, the antiderivative of that is the sine of 17 pi x squared plus 3 or something like that. I can't write that kind of thing down with our basic functions. Differentiation, if you can write it down with basic functions, you can differentiate it and get something with basic functions. Anyway, anti-differentiation is harder, but they're related very closely to differentiation. And anti-differentiation sort of adds up all those little pictures to get a big picture. And it's harder because it tells you more stuff. You're able to do more with it, which makes it harder. And differentiation is kind of the simple, that's the Calc 1 stuff. Anti-differentiation, Calc 2, the harder stuff. That's the big picture for calculus type stuff. Ran out of steam there. Ran out of things to talk about. So let's call that for today, unless you guys have questions. Okay, I will see you guys tomorrow. We'll talk about 4.8.